So I want to start this story where I seem to often start my thinking, which is at servile duality. And so roughly what this is it's two different groups acting on the same space in a nice way. So the space we're going to act on, I'm going to abbreviate V sub n for just some n-dimensional complex vector space. And I'm going to have GLN act on Vn in what I call the natural way. You should think about GLN here as being a bunch of n by n invertible matrices over C. And so the natural way to act on a vector is just by multiplying to the vector. We can have GLN act on the rth tensor power of Vn diagonally. And so what this means explicitly is that if we have some matrix A and we want it to act on a tensor product of R vectors, it will just act the same on each and every one of them. So this will look like an AV1 tensor all the way up to AVR. Okay. The second action on this tensor power is going to be one of the symmetric group SR. So SR is going to act on this rth tensor power by permuting factors, essentially rearranging our sequence of vectors. So sigma, a permutation in SR, is going to act on the sequence of vectors by rearranging. And we have to put like the sigma inverse in there just to kind of make sure we have a left action like we want. But essentially, these are our two actions on this space. Yeah, question? Yes.
The vector space. So, and you say G and N, they are matrices. So it means V and are in the form of the vectors, like 1, 0, 0 standard one.
So I want to think about this as C to the n. So these are these like column vectors. Yes, yeah. You could write all of this in a way that's sort of agnostic of basis, but I think it's going to be useful for us to just have chosen a basis. Okay, so these two actions, I think it shouldn't take too long to convince ourselves that these two actions commute with each other. It doesn't matter if we rearrange our factors before and after, if we're actually just applying the same exact matrix to each of them. But sort of the magic of this is that something even stronger is true. These actions are what are called mutual centralizers. What this means is that if I look at all of the endomorphisms of this tensor power that commute with the SR action, this is generated by the GLN action and vice versa. If I look at all of the endomorphisms of this tensor power that commute with the GLN action, this is generated by the SR action. Okay, so in a sense, these two actions determine each other. If you know what one of them is, you can figure out what the other one is by just asking, what's everything that commutes with this? And the important consequence of this when it comes to representation theory is that as a GLN cross SR module, this tensor power decomposes as a direct sum over integer partitions of R with length at most n into pairs of irreducibles, one from GLN, one from SR, that are indexed by that same partition. And so this sets up some kind of correspondence between an irreducible representation of GLN and irreducible representation of SR. Okay, so this is the idea of Servile duality, and this is the kind of duality I want to talk about. When we have these nice things that mutually centralize each other, we can draw a lot of information about the representation theory of one from the representation theory of the other. Yes?
Or that column vectors,
Say again?
the right hand side, W. Are there still here the column vectors?
This is going to be, let's see. In a sense, what I'm saying is that there's an isomorphism between these. You can choose however you want to construct the irreducibles of the symmetric group. My favorite way is via these standard Young tableau, this like Young construction. But I think these are isomorphic to each other. I'm not necessarily saying that you should think about these as column vectors. Okay. So I want to build on this notion of duality a little bit and talk about something called seesaw dualities. Okay. So what I want to do is I want to put this space in the middle, and I have my GLN action and my SR action here are sitting on opposite sides. They're dual to each other. And what I want to do is on this left-hand side, restrict from all of GLN to only the permutation matrices. So I'm restricting to a copy of the symmetric group Sn, which I want to think of as permutation matrices. And I want to think about, well, what commutes with that? What sort of sits opposite to this in the sense of duality? Well, it turns out to be something called, right, PRN. But before I describe it, I want to note something that we can kind of deduce immediately, which is if we are asking to commute with fewer things, we should have a larger set that commutes with it. We're kind of asking less. And so we should get something more. And this is where sort of the seesaw comes in. This idea where if you restrict down on one side, you go up on the other side. So whatever this looks like, it should have a copy of the symmetric group SR sitting inside of it. Okay, then I want to draw you a brief cartoon of what this PRN looks like. It's called the partition algebra. And I want to note with a brief caveat that this cartoon only really works if n is at least 2 times r. You need to have sort of a sufficiently large n. And so everything in this partition algebra looks like a diagram where you have r dots on your top and bottom, and you can connect them up however you'd like. So I'm going to connect them up like this. So we've got three dots in a connected component, these two connected, these three in a component, and then two on the top left on their lonesome. Okay, so this partition algebra is supposed to be somehow acting on this tensor space. And how it's going to do that is it's going to take in some tensor product of basis vectors, ei1, ei2, ei3, ei4, ei5. And now it's going to use all these lines to figure out what we should draw on top. So first, this picture is saying that ei1 and ei2 better be the same. If they're not the same, I'm just going to give up and give you 0. So I'm going to put a delta i1, i2 out front. So this is going to be 1 if i1 and i2 are the same, 0 if they're different. Same for i3 and i5, because those two are connected. And so I'm going to have a sum. I have ei1, ei2 propagate up to be ei1. This has no constraint, so it's just free. So I'm going to have some j that I'm summing over. ei4 propagates up. ei3 propagates up. And then finally I have some e k. That's free, so I'm summing over j and k. Let me just quickly reproduce that in a way that's not so cramped. I1, I2, delta I3, I5, sum over j and k of ei1 tensor ej, tensor ei4, tensor ei3, tensor ek. Okay. So this partition algebra consists of all diagrams that look like that, and this is sort of how you can have it act. And just like in this scenario, there's some correspondence between the irreducible representations of the partition algebra and irreducible representations of the symmetric group. And if you study this algebra, you can better understand the representation theory of the symmetric group. And so what I want to do now is give you a slightly more concrete example of what that looks like. Sort of what exactly can you try to study about the symmetric group? And so to do that, I want to tell you about seesaw reciprocity. Yes.
Or you make a subset of them Sn and Sr to commute, then you have the sure release them.
So what I'm saying in this picture is that the GLN and the SR commute, and the SN and the PRN commute. I'm not saying, well, in a sense, the GLN here, let's see, I would say the SN, you're not really saying much about what the SN and the SR are doing together, or those two, but because the SN sits inside GLN, this SN action will commute with the SR action. But you won't get sort of as much representation theoretic information because it's not, SN is not everything that commutes with SR. If you're asking for only some piece, this SN won't directly tell you about SR. Yes? Yes.
The ones that have a line going to the top.
Yes.
And then the one that's free is where there's nothing.
Yes.
How did you pick between the two going to I?
You chose either one because this sum is only ever going to actually come into play if, say, I3 and I5 were the same. Yeah, so I just chose the leftmost one to be consistent. Yeah, you could have chosen either. Okay, so what seesaw reciprocity tells you is that sort of given the setup, here I'm going to have a vector space V in the middle, K and K prime are Servile dual to each other. They're mutual centralizers. G and G prime are Servile dual to each other. And K sits inside G, and G prime sits inside K prime. So given that setup, we know a few things. One, we know that V decomposes as a G cross G prime module in this multiplicity-free way that pairs up the representations of G and G prime. The same is true for K and K prime. And then finally, the really interesting one is that hum K, I'm going to write this in terms of a bunch of hums, and then I'm going to actually tell you in words what's happening. So the homomorphisms from WK mu to the restriction from G to K of WG lambda is isomorphic to the homomorphism, the G prime homomorphisms from WG prime lambda to the restriction from G prime to K prime W K prime mu. Right, so both those restrictions should make sense because, yep, K sits inside G. Oh no, I think I want this one flipped, right? See, this is why it's always good to have that step where you check that everything you wrote made sense. Okay. So, yeah. Okay, so what this essentially means for us, the reason this is significant, the upshot, yes.
Saying that your reducibles are indexed by lambda, but should I be imagining partitions?
Oh, yeah. I think I actually want this to be muse here. But that won't be too different. So lambda and mu, they everywhere here, they're going to either be partitions or pairs of partitions. Yeah. But in general, they could be any sort of indexing set you want. Yes. Say again? Yeah, so these are as vector spaces, right? These have no more structure than vector spaces. Yeah, these concepts have no more structure than vector spaces. So really all we're saying is that the dimensions of these are the same. And so the upshot of this is that restricting from G to K is the same as restricting from K prime to G prime. Right, so if you want to understand how to do some sort of restriction, you can do it on either side. And so to your point, this isomorphism, this is just saying that these have the same dimension. In terms of representations, it's saying that the multiplicity of this irreducible in this restriction is the same as the multiplicity of this irreducible in this restriction. So if you can restrict on one side, you can restrict on the other side. Okay. How are we feeling about that? Okay. So now I want to introduce Kronecker coefficients into the story. To say, recall the diagonal action of SR on the tensor product of two SR irreducibles decomposes as WSR lambda tensor WSR mu is a sum over nu WSR nu with multiplicity G lambda mu nu where G lambda mu nu are called the Kronecker coefficients. Okay, and if you do a lot of work in combinatorial representation theory, when you hear Kronecker coefficients, you sort of tense up because these are really difficult things to understand. And so it's been a very long-standing question of, well, we know that these are all going to be non-negative integers because they count the multiplicity of some space. So we'd like to be able to sort of describe some kind of objects that you can count to figure out what that Kronecker coefficient is going to be. Okay. So what I want to do is use this idea of seesaw reciprocity to kind of get at these Kronecker coefficients and show you an example of what that looks like. Okay, so we're going to look at Kronecker coefficients through the partition algebra. And so this is work by Perlman, De Vischer, and Mariana in 2012. And so what they did is they sort of took this Servile duality between the symmetric group and the partition algebra and sort of doubled it in a sense. So what they did is they took this space that's R tensor copies of Vn and then S tensor copies of Vn. And they said, well, I could just have a copy of Sn act on each of these. So Sn cross Sn acts on this. If I do that, then I just get a copy of Prn and Psn. So then I can also take this tensor product, very much like a regular product. I have these two exponents, same base, I can combine them. So this is Vn to the R plus S tensor power. And if I have just one copy of Sn acting on that, what do I get on the other side? It's this PR plus Sn. And so if we turn it into sort of this seesaw picture, we've got sort of this vector space in the middle, which I'm just going to call V for brevity. We have Sn cross Sn. Sitting dual to that is this PRN cross PSN. And sitting inside this Sn cross Sn is this diagonal copy of Sn. Dual to that is this PR plus Sn. Okay, so we have this seesaw duality picture combined with this description of Kronecker coefficients as this diagonal action. We can sort of find Kronecker coefficients in the representation theory of the partition algebra. And so how we do that is we say that G lambda mu nu this is the dimension of this Hom space, I guess this Sn Hom space, from Wsn nu to the restriction from Sn cross Sn to Sn of this Wsn lambda tensor Wsn mu. Right, so all this is really just saying this in slightly different language. Then by the seesaw reciprocity, this is the same as mentioned of the Hom. Let's see, this is going to be for P R n cross PSN. WPRN lambda tensor WPSN mu restriction from PR plus Sn to PRN cross PSN. This irreducible for PR plus Sn. Okay, so restriction of that. Okay, so what does this mean? This means that Kronecker coefficients show up in the restriction of partition algebra modules to what the authors called Young type subalgebras. And I can draw you a picture of what that looks like. This Young type subalgebra is just saying I have diagrams where I've sort of drawn a line between my first R and my last S dots, and it's saying that I'm not allowed to cross that line. So essentially I have two pictures, one for PR, one for PS, that are just juxtaposed together. Okay, so then sort of the punchline here is that Bowman, Divischer, and Oriana sort of exploit this fact to compute formulas for reduced Kronecker coefficients where one partition is either a hook shape or has two parts. We're not going to worry about what the reduced here means. There's some kind of like stability that happens in this representation theory as you let the partitions get really big. And so they computed things in sort of this limiting case. And part of that has to do with this fact about n needing to be at least 2r. Okay. So the upshot so far is we have these dualities. I'm particularly interested in this sort of setup, the seesaw reciprocity, where I can take on the left-hand side this restriction that gives us Kronecker coefficients and have something on the right-hand side where we can translate this problem of Kronecker coefficients into another representation theoretic problem where we can maybe make some progress. Okay, I want to give us a short break. If you have a question, yeah.
Note that reduced adjective, these coefficients were known combinatorially, right? So do they get more reduced coefficient? I mean, the hook shape is Jonah, but that was off. I don't know.
I can't remember when Jonah Blasiak did the hook shape. I don't remember the relationship here. But I'm also not sure about the two-part, because I know that Rosa had the two-part one, and I have a date later in the talk that I'm certain is before this one.
So my question is that reduced thing thrown in, you actually get more.
I think you do get a little bit more here, because I believe what they're doing is they're putting a hook shape in and then introducing a long row on top. So it is a different shape than the one that's known. Okay, I want to give us a brief break, maybe just a couple of minutes, but if you have a question. The ERPs of partition algebra? Yeah, so for the symmetric group, the ERPs look like these standard Young tableau. For the partition algebra, they're also indexed by integer partitions. We can see that because of this duality. And so you would expect them to have bases indexed by some kind of tableau. And in fact, they do. It's just instead of tableau filled with the numbers 1 to n, they are filled with sets. So they're set-valued tableau, where the numbers 1 to n all occur. So what that looks like, so if I have, say, W, I'm going to do this one. P 4, 8. Then we have a shape like, so we should do something like 4, 3, 1. You get tableau, shape 4, 3, 1, where you can have some empty boxes, and then you start filling this in with the numbers like 1, 2. I guess I didn't really give myself a lot of room here. We're going to up this slightly. 3, 5, 4. So suddenly you're able to have sets of numbers in here. Yeah, so it's a really similar construction. So there's a similar straightening algorithm to how things worked for the standard Young tableau for the symmetric group. Yes.
equation for defining the Kronecker
Yes.
coefficient, and it is under cover the coefficient.
So you can write this in different ways. Some people will put the coefficient in front to indicate it's that many copies. But because I'm doing lots of like tensor powers and then also these direct sums, I wanted to kind of write them similarly. But you could write it out front, people would know what you mean. Okay, I want to move into part 2 here. And I'm going to start it with a really similar example to what we did here with the partition algebra. I want to replicate this but now I instead want to think about Kronecker coefficients through GLN. So here we used this duality between the symmetric group and the partition algebra, but we had this even earlier duality between the symmetric group and GLN. So what we want to do is we want to start with this Schur-Weil duality and sort of double it in the same way that they did over there, where I have a Vn to the rth tensor power, tensor Vm to the rth tensor power. I have 2 copies of the symmetric group SR acting, so I should get a copy of GLN and a copy of GLM acting. But like here, where we had sort of same base, different exponents, we combined them. Here we have the same exponents, different base. So this is going to be I'm going to write this as Vn tensor Vm to the rth tensor power. But I want to think about this as just now an n by m dimensional space. And so now I want to act by a single SR. And so then over here, I end up with GLNM, applying this Schur-Weil duality. And so now we have this space in the center. I have my SR cross SR restricting to this diagonal copy. Sitting on the opposite side is this GLNM restricting down to this GLN cross GLM. And so this means if we want to understand this Kronecker coefficient, G lambda mu nu, this is just the multiplicity of WGLM lambda tensor WGL, sorry, I should do GLN, GLM mu in the restriction from GLNM to GLN cross GLM of this irreducible W nu.
When you realize the inclusion is just by the tensor product of
Let's see. Yes. Yeah. Because what we're doing is literally combining the Vn tensor Vm into this. Okay. So just like here, we restricted down to sort of this picture, these Young subalgebras where we've drawn this line. Here, somehow we're supposed to take a GLNM module and restrict it to a GLN cross GLM module. So we have a really useful tool for trying to handle representations of these classical Lie algebras, and that is crystals. So I'm going to proceed to not exactly tell you what a crystal is, but tell you enough of what a crystal is. So combinatorially, we're going to think about a crystal as an edge-labeled graph. Now, there's a lot more data that goes into this, a lot more axioms, but we're only going to need essentially one kind of crystal, so I'm just going to show you what that crystal looks like. And you have all the information you need to think about this. And that example is a crystal on words. Here are vertices are going to be words with letters 1 to m of length k. And we're going to have edges to w for all I and m minus 1. Okay. We're going to have edges labeled 1 to m minus 1.
Guys, would it be possible to change the camera?
Yes?
remove the camera.
Thank you.
In several ways.
You probably asked the message first. I know what I think about.
Okay, so this is how we're going to transform a word. So we're going to have a word like, for example, 1, 2, 2, 3, 2, 4, 3, 4, 1, 2, 3. Okay, and what we're going to do is we're going to apply f sub 2. First, we're going to replace every 2 with a closing parenthesis, every 3 with an opening parenthesis. And we're going to kind of ignore the other numbers. So we have some number, close, close, open, close, some number, open, some number, close, open. Then we're going to match parentheses. These two match. These two match. We are going to flip the, let's see, want the leftmost unmatched closing parenthesis. So that should be this one here. So it becomes an open. I think I want rightmost. Yeah, everything I will say will be true up to switching some direction. Okay, so that one will stay the same. The rightmost unmatched one. And then we translate back to numbers. This is going to be now 1, 2, 3. 3, 2, 4, 3, 4, 1, 2, 3. So I've taken my word. I've done this process to select a number I and turn it into an I plus 1. Okay, and so I said that would be our only example, but I'm going to give you a second example. But if you squint, they actually are the same example. See, so this is crystals on Tableau. And so what I want to do is I want to take a semi-standard Young tableau. I want to read its entries. And when we write it in the correct orientation like this, reading the entries is very simple. Just like reading a book, left to right, top to bottom. So the corresponding word here is 211. If I apply this process, this parenthesization, for F1, I'm going to change one of these ones to a 2. It turns out to be the last one. And so now I get the tableau whose reading word is 212. And so I could keep doing this in all the ways that I can. So here I have 2, so I'm going to end up with changing a 2 to a 3. This is a 2, so I change one of the 2's to a 3. It's going to be 1, 3, 2. See, 3, 1, 3. Three, 2, 3. Okay, if I go through and apply this process to all the words, I arrange these tableaux into this directed graph structure. Okay, how are we feeling right now, kind of about computationally how we did that? We have this parenthesization process, and now we're applying it to the reading word of the tableau, which we read just like a book, left to right, top row to bottom row. Okay, so now what's the significance?
So sorry again. Can we change the camera?
Yes, we can, Hunter, please. Okay, so what's the significance here? How is this going to help us understand these representations? Well, vertices in the crystal correspond to basis vectors of some GLN representation V, connected components, so like one that I drew up here, correspond to irreducible reps, let's say, occurring in V. And so if we're able to take a representation we want to understand, V, and put this crystal structure on it, then the connected components of that crystal structure, I'll be able to identify like, oh, this connected component is sort of this shape, so I know which representation it is. I'll say each connected component is determined by something called its highest weight vector. Yes. Let's see. Here, N is M. Right, so this is a GL3 representation, because I could go up to 3. Okay. So I want to say one more word about this highest weight vector. So this highest weight vector, let's see, highest weight vector, I'll just continue the sentence. Whose reading word is a property called Yamanouchi. Yamanouchi just means every suffix has at least as many ones as twos, twos as threes, and so on. So here, this unique one is actually this 2, 1, 1. You can tell if I look at the end, I get 1. If I look at the last 2, I get 1, 1. Look at the whole thing, I get 1, 1, 2. At no point did I have more 2s than 1s. Okay. So we had this idea of somehow we can put a crystal structure on something, and if we can do that, then our connected components tell us how to decompose it into pieces. And we can think about that as somehow we assign a word to all of our combinatorial objects, and it's precisely the ones with Yamanouchi words that are our highest weight, and so it's determine each of our connected components. Okay. Now let me say, what does this mean if I'm trying to break up something that's a GLN cross GLM representation? So here I'll say that W GLNM new has a GLNM crystal structure. And we actually understand that structure really well. But now to decompose it, as a GLN cross GLM module, we want commuting GLN and GLM crystals. What that means for us, do you want to hit the next board? Is rather than just these operators Fi, is we want operators F super I for I and n minus 1, F sub I and m minus 1, where Fi Fj is the same as Fj Fi. So somehow these F super I's, these are crystal structure as a GLN module. These F sub I's are crystal structure as a GLM module. And to decompose it as this GLN cross GLM module, we need these two things to commute with each other. Okay, and if we could do this, we could solve the problem. So obviously, we can't quite do this yet. But what I want to do to finish the talk is to introduce a combinatorial object that we think is very useful here and sort of describe how we can make partial progress towards this. I really overestimated how easily that would slide up. Okay. So I want to talk about a combinatorial object that we're calling bitableau. So there's something called bitableau in the literature. It's pairs of tableau. That's different than this. This is the right thing to call bitableau. That's just pairs of tableau. So where
Is this
Yes.
Rota? Is this Rota's by Tableau, or does this Rota have it wrong?
Rota's wrong? Yes. Um, okay. On that note, so I first kind of want to show you how this naturally falls out of the representation theory. So I'm going to say recall the Schur functor S lambda, where S lambda V has a basis indexed by semi-standard tableau filled with basis vectors of V. So again, here I've chosen a basis for my space V, and S lambda of V has a basis indexed by semi-standard tableau, which are filled with those basis vectors. If we think about WGLNM, nu, this is the space we want to study, this irreducible. This is the same as S nu of this Vn tensor Vm. Yes, exactly. We're going to fill it with pairs. And so this basis, as Nantel just spoiled, is indexed by pairs in n cross m. Lexicographically. And so what this means is that this space we want to study, this representation W nu GLNM, has a basis indexed by what we call lexicographic bitableau, or just bitableau for short. I'm going to write B nu N M, where nu is our shape, N is max for what I'm calling top entries, and M is max for bottom entries. And it'll be clear why I call them top and bottom in a moment. So as an example, we have 1, 1, 1, 2, 2, 1, 1, 2, 1, 3, 2, 1, 2, 1, 2, 2. This is an example of a lexicographic bitableau of shape 3, 2, 2, 1. Top entries max out at 2, bottom entries max out at 3. Yes.
Is this your result?
I mean, it's not really a result yet, is it?
I mean, this is just about bases. So you have a space,
Mhm.
you find a Schur functor,
Mhm.
and you're saying that you get a basis indexed by these guys.
This, in a sense, is just the definition of the Schur functor, if you choose my definition of the Schur functor.
Okay.
Right. In a moment, I'll state something that's actually a result, and then we can maybe talk about that.
To explain what is the
Mhm.
the GLM crystal.
Yes, yeah. Yeah, so there is some subtlety in like how you put the GLN and the GLM in, but you're essentially doing this as the tensor product of matrices, and you work out the combinatorics there. Okay. So let me then state kind of our refined goal. Now sort of in terms of these bitableau, we want a GLM cross GLN crystal structure on bitableau, where we have this Fi for I in 1 to n minus 1, where this raises a top entry I to I plus 1, and Fi for I in 1 to n minus 1, where this raises a bottom entry I to I plus 1. So in a sense, our commuting structures on these bitableau want to sort of act on the top entries and the bottom entries separately in a way that commutes.
So, can I ask a question?
Yes.
Sorry, one way also to do that, I'm not sure, but you know, like you're looking to ONM, I see.
Yeah.
Because somehow the FN that you excluded there is
Yeah.
what makes everything commute.
Let's see. In a sense, yeah. But we need to sort of exclude that to restrict down to this particular thing. Yes.
The second question, like,
Uh-huh.
since you can also, instead of restriction, you can also induce.
Uh-huh.
Have you looked at the other one?
We've not looked at the induction, but I mean, that would be sort of equivalent in solving our problem, but might also give us some insights on some interesting combinatorics we can look at, for sure. Okay, so what I want to close with is essentially just telling you how we've done one of these two things, which very generously is halfway done, but really isn't anywhere close to halfway done. But essentially we have, I'm going to say, we're going to describe a GLM structure that we think is a good candidate to be half of this answer. I'm going to leave that business up there. Okay, so this will be a GLM crystal on bitableau. Okay, so given T, some bitableau of shape nu, max entries n and m, we're going to let Wi of T be the result of reading the bottom entries of boxes of the form I on top, something on bottom. So it's like I have a reading word like I had for my Tableau earlier, but I'm saying only read the ones where the top entry is some prescribed number. I'm going to let W of t be the concatenation of all of these. So W1 of t, W2 of t, and so on. So let's see what an example would look like. So let's use this t up here in this example. So this up here is our t. And so in this case, W of t, we're first going to focus on just the boxes whose first entry is 1. So that forms this 2 by 2 square. If we read off the bottom entries, we get 2, 3, 1, 2. Right, that's my W1 of t. Then if I focus on the ones with top entry 2, I read from the top 2, 1, 1, 1. Okay, so this is my word W of t that I've extracted from this by Tableau. So note that if I apply this parenthesization operation to this word, 2, 3, 1, 2, 2, 1, 1, 1, for F2, I should end up with 3, 3, 1, 2, 2, 1, 1, 1. So I've chosen one of these 2's to raise to a 3 using parenthesization. So what this means is if I take this by Tableau, one, 1, 1, 2, 2, 1, 1, 2, 1, 3, 2, 1, 2, 1, 2, 2. How I apply this raising operator to is taking wherever this corresponding 2 was, wherever I read it, and changing it to a 3. And that so happens to be this 2 right here. So that 2 becomes a 3, and everything else stays the same. Okay. So somehow I have a way to do this crystal operator on this by Tableau. Wouldn't be great? um, and so the reason we like this construction is this is a GLM crystal structure that preserves the GLN weights. Right? This is something that's absolutely necessary if you're going to want two things that commute. What this means combinatorially is just that I don't really mess with the top entries. It's the same sort of multi-set of top entries that are there. And this is enough to state a technical result. So you can tell who it's by, because I put who it's by. Which is that if you want to take the Kronecker product of Schur functions, S lambda and S nu, and expand it in the monomial basis, let's say d lambda mu nu, you can describe this in terms of bitableau. So that coefficient d lambda mu nu is the number of bitableau T of shape lambda with top entries given by mu bottom entries given by nu, and this reading word Yamanouchi. Right? Because effectively what we've done here with this crystal that preserves the GLM weights is we've explained how this breaks up into weight spaces, which is exactly what you need to have this monomial expansion.
The monomial expansion knows the dimension of certain invariant spaces under Young subgroup action. So if I fix an M mu, I've got a representation, and I'm looking at its S Young subgroup mu invariant space. Is so going back to some of the stuff you had on the board earlier, like dimensions of harm spaces,
Yes,
and the like. Is that why you end up here, or I'm
yeah, so
jumping several steps?
You end up here because this is telling you how many like semi-standard tableau you have of a particular weight. Right? Because if you can organize all these MUs into the S's, then you've actually figured out how it decomposes as a representation. This is just telling you how it breaks into the weight spaces. Yeah.
Exactly. So generalized. So what happens if you take more factors of GL?
Take more factors of GL. Right. Yeah, so that's going to get you into like these, I don't know what people call them, but essentially you have like these like sort of bigger Kronecker coefficients where you're saying, I want like 10 different SR representations and understand how that decomposes. So yeah, you could do that, and that would get you to these larger ones. Okay. So, yeah, sure.
If n is equal to 1, then
Right.
you can do it.
Yeah, I think we can do that if n equals 1.
So can you, does that give you new result on the for the Kronecker?
I think that it shouldn't, because what that's going to do, yeah. Yeah. So I think that that won't be very interesting here. Essentially, what it's doing in terms of the combinatorics of the bitableau is it's saying, set all the top entries to 1. So really, morally, you just have a semi-standard tableau. What's more interesting is, say, if you set n equal to 2, then you start having actual interesting things that you're trying to understand. So we have understood some.
Yes.
And so I'm going to say I don't have a lot to write down for this, but what I'll tell you is, so there are two interesting results for when you have a partition of length 2. One of them is, let's see, who was it? It was, I think, yeah, Ballantine Oriana in 07. They created these things they call Kronecker tableau. And then Mike and Rosa had something with their inhomogeneous bases where they described these multi-set valued tableau. And basically, what we want to do then is we want to put a GL2 crystal structure on these things. And as we were trying to put that structure on, it looks like the Kronecker tableau are going to be the lowest weight, and Mike and Rosa's tableau are going to be highest weight. So we can describe what it should look like at the extremes. And so we're trying to figure out, well, how do you get that full GL2 crystal structure? In addition, those two results are sort of in this like reduced case where you have this long first row. And so we're hoping that we can push on that and actually get all of the length 2 Kronecker coefficients by trying to complete this GL2 crystal. But that's essentially what I wanted to say in my closing remarks, is that we have this sort of paradigm that we like, these bi-tableau. We want to figure out these crystal structures. And part of why we like it is that a lot of results seem to fit very nicely into it. And so, for example, we can like unify these two examples of this length 2 as being opposite ends of this GL2 crystal. And then you can sort of very easily describe what, say, like a 1-row shape or a 1-column shape are in terms of this like RSK crystal and this like dual RSK crystal. And so that's why we're so excited about this, is it's like we like this sort of framework and we can fit a lot of known results into it. And we're trying to sort of push on what this can do. Yeah, Mike?
So what seems to be missing by tableau picture is some sort of operation where you swap
Yes.
the first detected entries and then resort
Yes.
in such a way that it's an involution.
Yes.
And have you tried pushing on?
Yes. So we've sort of come up with some involutions, but it's the sort of thing where we're like, okay, we're kind of playing some whack-a-mole. We're like, okay, if we fix that involution and we fix this GLM crystal structure, how many GLM crystal structures could there possibly be? Still a lot. But if we're like trying to figure out like, well, if we have each of these pieces, which is like a GLM structure, a GLN structure, and some way to do this like conversion by swapping the weights.
Want to say that F lower I is equal to involution.
Yes.
I,
Yes.
that doesn't work.
Well, it's like you can kind of define that, but then you have to actually figure out what that other operation is, because you have to be able to describe that operation to know what the like highest weight vectors are. Right? So we can say like,
The involution.
so what the involution sends things to, what the F upper I is going to be. And so you can define like F upper I is going to be just conjugate this F lower I with some involution.
No, it's not going to start a row. It's going to have to be, some operation which sorts the whole tableau
Mhm.
in such a way that if you do it twice,
So our best kind of guess at what that maybe should look like is there's this this conversion due to, I think Heyman uses it, but essentially you're doing these like Bender-Newth moves to sort of change the order of your tableau.
well,
But you can change it from like lexicographic to reverse lexicographic and then swap the entries. Mm-hmm.
because the weight, the total weight first.
Mm-hmm. Yeah, I'm not sure.
I mean, ideally, you have one where it works no matter what your order. You just change your order and then restore it. And then
Yeah. Yeah.
Possible. Great. I don't know if you have you played with these operator can by Tableau?
Yeah, so we've like played with this, but we're kind of running a situation where we just have so many choices to make that like we need to think harder before we have any like productive play happening. Where we have like so many choices you could make, so many different ways you could try to reorganize things. Yeah. Yeah, but I think where we're most interested right now is trying to complete this GL2 crystal picture. Because I mean that's reasonably tractable because we know now what we want our highest and lowest weights like Tableau to be. We just want to figure out how to move between them to actually complete this structure so we have more examples of what the crystals on by Tableau should look like.
Now for questions.
Yeah, now are there any questions?
Get 2 rounds of applause is at least. No. I have a question.
Yeah, Leslie?
Is it true? Do I remember correctly that the LR coefficients are a subclass of the reduced Kronecker curve?
Yes.
So, do you get LR rules which are different than known LR rules from working in this framework?
That's a good question. We haven't really,
You know the answer,
yeah.
at least you know what you're going towards. Like, could
Yeah.
you fiddle and at least recover?
That's a good question because we haven't really like thought much about what comes of the combinatorics in that sort of reduced case, in this like limiting case. And so that could be worth at least an afternoon to think about like, well, what did the Tableau look like when you let this first row get very long? And then what should like, yeah, the Littlewood Richardson case look like in that situation? Interesting.
Other questions? All right, let's thank Alex again.